In this segment, we'll talk about an example of using bisection method to solve a nonlinear equation. So the example which we're asked to solve is to find the root of this equation right here. And we are supposed to use the initial bracket to be 1, 4. We're supposed to conduct 3 iterations. We're supposed to find the absolute relative approximate error at the end of each iteration. And based on that, we're supposed to say that, hey, how many significant digits are at least correct at the end of each iteration? So before we start applying the bisection method, what we have to make sure is that the equation is given in the form of f of x equal to 0. We are given x cubed equal to 20. So the first thing which I have to do is I have to rewrite the equation in the form of f of x equal to 0, which turns out to be x cubed minus 20 equal to 0, because that's what the algorithm is written for. It's written for equations which are of the form f of x equal to 0. Then also we are given that, hey, the initial estimates, not initial estimates, but the initial guesses for the bracket are given by 1, 4, that the root is lying between 1, 4. That's what it means, the lower limit and the upper limit of the guess of the root is given as this. But before we again apply the iteration, we've got to make sure that this bracket here, this bracket of 1, 4, is a valid one. So let's go and see if what is the value of the function at the lower limit will be 1 cubed minus 20, that's minus 19. What is the value of the function at the upper limit, which is 4? So it will be 4 cubed minus 20, and this turns out to be 44. So this gives us that the value of the function at the lower limit multiplied by the value of the function at the upper limit is minus 19 times 44 is less than 0, which basically then tells us that the 1, 4 initial bracket is valid. So because it means that the function is changing sign between 1 and 4, that it is going through the x-axis. So that makes this initial bracket of 1, 4 to be valid. And now we are ready to conduct iterations. So let's look at iteration number 1. We have our lower limit to be equal to 1, upper limit equal to 4. So that gives us the midpoint between the lower and upper limit will be xl plus xu divided by 2, which is 1 plus 4 divided by 2, and that's 2.5. So that's the first estimate of our root. This 2.5 is the first estimate of our root. Can we calculate epsilon? Can we calculate the absolute relative approximate error? No, we can't. Cannot be calculated because we don't have a previous estimate of the root. We only have a new estimate of the root, but we don't have a previous estimate. So that's the end of the iteration 1. Let's go and see what happens for iteration 2. So iteration 2, what we're going to have is as follows. Our xm is 2.5, we just found out. So let's go and find out what the value of the function at xm is, which is the value of the function at 2.5, which will be 2.5 cubed minus 20, and that number turns out to be minus 4.375. Keep in mind that now what we have to do is we have to see whether the function at the lower limit times the function at the midpoint now, what is the sign of that? We know that the lower limit is 1, the midpoint is 2.5, which we just found out. And what is the value of the function at 1? It's minus 19. The value of the function at 2.5 is minus 4.375, which means it is greater than 0. What that means is that the function does not lie between 1 and 2.5 because it is not changing sign between 1 and 2.5. So what that means that we had 1 and 4 and we had 2.5, right? So it is not between these two numbers. So it has to be between these two numbers where the function changing sign. So this becomes my new lower limit, and the upper limit stays the same. So we'll have XL equal to 2.5 and XU equal to 4. And what this does is that this gives me the new estimate of the root to be the midpoint between XL and XU, the redefined XL and XU, and that turns out to be equal to 3.25. Now what I want to do is I want to calculate what the absolute relative approximate error is, which will be the current approximation, which is 3.25, minus the previous approximation was 2.5, divided by the current approximation 3.25 times 100, and this number here turns out to be 23.1%. Now if I want to find out what is M is, what I mean by M is what is the number of significant digits which are at least correct in the estimated root of 3.25, it'll be 0. So 0 number of significant digits can be at least trusted in my solution of 3.25 because the absolute relative approximate which I get is nowhere close to 5%, because we know that if it is less than or equal to 5%, we can claim at least one significant digit to be correct. If it is 0.5%, then we can claim 2 to be correct. If it is 0.05, we can claim 3 to be correct, so on and so forth. So in here, we cannot claim any of the significant digits to be correct as epsilon A is greater than 5%. Let's go and see if we have any better luck with the third iteration. So let's look at iteration number 3. So in iteration number 3, what I have is that my XM, which I just found out, was 3.25. So the first thing which I have to do is I have to find the value of the function at this midpoint, which I found from the previous one. So it turns out to be a quantity which is 14.33. And if that is the case, what is then the multiplication of the function value at the lower and the midpoint, lower limit and the midpoint would be equal to, hey, what was the lower limit in the previous one? It was 2.5. What was the midpoint now, which is 3.25? That gives me that 2.5. It was minus 4.375, and at 3.25 I just found out, and this turns out to be less than 0. So what that tells me is that I had my 2.5 and 4 as my lower and upper limit. My midpoint was 3.25. I found out that, hey, the function is changing sign between 2.5 and 3.25, as is the case here. So that means that the root does lie between this new bracket now of 2.5 and 3.25. So if that is the case, this becomes my lower limit and this becomes my upper limit. So let's write that down. The lower limit is 2.5, upper limit is 3.25, which gives me that the estimate of the root is now the midpoint between these two. And this number here turns out to be equal to 2.875. So that is my value at the end of the third iteration. Let's go and calculate our absolute relative approximate, which is the current approximation minus the previous approximation divided by the current approximation. And if I multiply by 100 to get the value in terms of percent, I get 13%. And what I'm finding out is this 13% is still epsilon A is greater than 5%. And so I still will have to say I cannot trust any of the significant digits in my solution right here. So what you got to think about is that we'll have to conduct even more iterations to be able to get this number to be down, so that we can start trusting some significant digits in our estimate of the root. But also gives you a glimpse that although bisection method is guaranteed convergence, because you know that the root lies between the lower and the upper limits of your bracket, but the convergence seems to be slow. And that is the end of this segment.